Welcome back to the Data Analytics series. Today, we'll explore regression analysis, a foundational technique for predictive modeling. We'll start with simple linear regression, then move into multiple regression, and finally discuss advanced techniques such as polynomial regression and regularization. By the end of this video, you'll have a clear understanding of how to build and evaluate regression models. We will be looking at the following contents in this video. Regression analysis is a statistical method used to model the relationship between a dependent variable, often called the target, and one or more independent variables, known as predictors. The primary goal of regression is to predict the value of the dependent variable based on the values of the independent variables. There are various types of regression techniques. Simple linear regression models the relationship between two variables. Multiple linear regression deals with more than one independent variable. Polynomial regression is used when the relationship between variables is nonlinear. Logistic regression, although technically not a regression method, is used for classification tasks where the outcome is categorical. Simple linear regression models the relationship between a single independent variable and a dependent variable by fitting a straight line to the data. The equation for this is y equals beta 0, the intercept, plus beta 1, the slope, multiplied by x, the independent variable, plus an error term. This equation allows us to predict the value of y based on x. In this formula, beta 0, or the intercept, represents the predicted value of the dependent variable when the independent variable is 0. Beta 1, the slope, tells us how much y changes for each 1 unit change in x. Understanding the coefficients is crucial for interpreting your regression model. The intercept, beta 0, is the starting point for your predictions, while the slope, beta 1, quantifies the relationship between the variables. A positive slope means that as x increases, so does y, while a negative slope indicates that y decreases as x increases. Multiple linear regression extends the simple linear regression model by including more than one independent variable. The equation is similar but includes additional terms for each predictor variable. This allows us to model more complex relationships between the dependent variable and several predictors. When performing linear regression, certain assumptions must be met to ensure valid results. These include linearity, meaning the relationship between variables is linear, independence of observations, homoscedasticity, meaning the variance of errors is constant across all levels of the independent variable, and normality, which assumes the residuals are normally distributed. To evaluate the performance of a regression model, we rely on several metrics. R-squared tells us how much of the variance in the dependent variable is explained by the independent variables. Adjusted R-squared adjusts for the number of predictors, penalizing models that include unnecessary variables. Our MSE and MAE measure the average error between the predicted and actual values, giving us a sense of how accurate the model's predictions are. A common challenge in regression modeling is finding the right balance between overfitting and underfitting. Overfitting occurs when the model is too complex and performs well on the training data, but poorly on new data. Underfitting happens when the model is too simple to capture the underlying patterns in the data. The key is to find a model that generalizes well to new data. When the relationship between the dependent and independent variables is not linear, polynomial regression can be used. By adding higher degree terms to the model, we can capture more complex patterns in the data. The formula extends the linear regression equation by including terms like x squared, x cubed, and so on. Regularization techniques, such as lasso and ridge regression, help prevent overfitting by adding a penalty term to the model. Lasso, or L1 regularization, adds a penalty based on the absolute value of the coefficients, driving some coefficients to zero, which effectively selects variables. Ridge, or L2 regularization, adds a squared value penalty, shrinking the coefficients but keeping all variables in the model. Let's now see a practical example of building a linear regression model in Python. We'll use house price data with features such as the size of the house, the number of rooms, and the location to predict the price. We'll use popular Python libraries like pandas, numpy, scikit-learn, and matplotlib to build and evaluate the model. We will be working on this collab notebook, and our file is also stored in this, as you can see in the file section. This will be our Python code that will help us build a linear regression model. Our first step is importing the required libraries and our dataset. You should change the path of the dataset according to you. Then we will clean the price column, remove $ and commas, convert it to float. Next step is preparation of independent variables, x, and dependent variable, y. Split data into training and testing sets and build and train the linear regression model. Next, we will make predictions and evaluate our model. We will be calculating the values for root mean squared error and our square score. At last, we will use matplotlib to visualize the actual versus predicted prices. Time to test our linear regression model. And here we get value for our MSE and our square score, as well as it plots an actual versus predicted houses prices scatter plot. As you can see in this scatter plot, majorly the values are concentrated along the line, but some values are below and beyond. Such values are known as outliers of the dataset. That concludes our exploration of regression analysis. In the next video, we'll dive into logistic regression and classification models, which are essential for making decisions when the outcome is categorical. Be sure to subscribe and hit the notification bell to stay updated with our latest tutorials.